Transformations of functions. So in today's discussion, we have some of the major ideas of our course. They apply to every chapter of our course, and that is the idea of transforming functions. In general, there are two ways that we may transform functions. The first is to translate them, and we can translate them horizontally, that's side to side, or vertically, that's up and down. So here are some examples. If I start with some function y equals f of x, and then I apply a horizontal translation, I just subtract d from x. In the brackets there, every x has d subtracted from it, and that moves the entire function d units to the right. We'll see this soon enough when we do some examples. Vertical translation, if we would like to move the function up, we add c to the function, where c is some number greater than 0, and that will move the entire function up. And there's a y there. There we go. Now compressions and stretches, horizontally, if we would like to compress our function, we multiply every x by the value b, where b is greater than 1. And it's going to compress the function so that each point is b times closer to the y-axis. Meanwhile, in a vertical stretch, we have a out front, a times f of x. And in this case, every point is a times further from the axis when a is greater than 1, where a is greater than 1. So there we have compressions and stretches. So now what we would like to do is to go through some specific examples for all the types of functions in our course. So the function types that we have here are polynomials, and here are some examples. Then we also have trigonometric functions. Today we'll just look at the sine function. And then we also have exponential functions. And for each of these, we'll take a look in the Desmos program. So let's go back to our first idea, or first type of function, that's polynomials. So here we have an example of a polynomial function. This is a quadratic equation. It is second order. The highest power of x is 2, because we have an x squared there. So this function is y equals x squared plus 5x minus 1. And that's our function f of x. So if we would like to now apply a vertical stretch, we multiply every value in the function by a. So if a is equal to 3, then we see here, we have a 3 out front here, and then we multiply 3 into x squared, 5x, and negative 1, and that gives us 3x squared plus 15x minus 3. There's our vertical stretch. So what does that look like now in Desmos? So we'll try here. It would be interesting to know if we can just copy this into Desmos. I don't know if we can. Oh, not quite, but we'll just do exponent 2. It almost copies right into Desmos. Okay, so there's our function. Now we'd like to multiply it by a factor a. So we can enclose the whole function in brackets and just put an a out here. And we're going to add what's called a slider. So there's a slider, a is 1, and now we go up to a equals 3, just like we did in our equation there. There's a equals 3. We can zoom out, move in here, and then zoom back in and see our function. There, it goes down as low as almost negative 22, somewhere around x equals negative 2.5. There's the lowest part of the function, and it comes up here, and it crosses the x-axis near x equals 0 and near x equals negative 5. Those are the two roots of the function. So if I make a back to 1, there's the original function, and if I multiply it by 3, now each point is 3 times as far from the axis. I can zoom out here and also see, well, what if a is negative? When a is negative, our parabola goes upside down. And the greater I make a, the more steep the function gets in both directions. So there is an example of a vertical stretch. Now, to show that this function is the same as the other one that we had in our document here, we'll try plotting this function now and show that they're actually the same function. So I'll just do y equals x, or 3x squared plus 15x minus 3. And look at that, those two functions are identical. If I make my a slightly different, you'll see that they are very similar, but when I make a3, they're the same function. Okay, so that's the first example, a vertical stretch on a polynomial. We just multiply each value in the polynomial by a number such as a, where a is equal 3, and then you get a new function. So that's the vertical stretch. Let's look at the horizontal compression. We start with the same function, y equals x squared plus 5x minus 1, and now each value of x we multiply by b. Okay, so then that becomes this expression here, b squared x squared plus 5bx minus 1. And if I put a slider in and let b equals 3, we'll get this function again. So let's try that. First of all, I'm going to try putting in b squared x squared plus 5bx minus 1. And we do that right here. So b squared x squared minus 5bx minus 1. Is that what it was? Oh, plus 5bx minus 1. And there's a slider b. Since I put a b there, it's nice. So b is 1. There's the original function. In fact, I can erase the function we're just using. Okay, and now we saw before that b was equal to 3 in our example. So we slide it up to 3. There's the function. And we can show that that's equal to 9x squared plus 45x minus 1. And put this as a square. And there we have it. So as we slide b, we see, oh, whoops. I just accidentally made that into a subscript. So we make it a superscript. There we are. Okay, so there's 9x squared plus 45x and minus 1. Is that what we should have had? It actually should be 15x there. Sorry about that. So we'll put that 15 in here. Okay, there, now we have the same function. So when b is equal to 3, we have this function, and they line up. When b is equal to 1, there's the original function, which is x squared plus 5x minus 1. So by multiplying everything by b, every x value by b, each point is b units closer. So here, if I look at the vertex, which is the lowest point, so from here to here is 1/3 of the distance, 1, 2, 3, to here. Each point is 3 times closer to the axis. And the point where they cross the y-axis here is going to be the same for each function, because this is 0 from the y-axis, and for the other one it's also 0, because 3 times 0 is 0. So each point is 3 times closer. So that's in a horizontal direction. So this point here is negative 2.5, and this one should be 1/3 of negative 2.5, which is negative 0.833. So there's a horizontal compression. I can make this go more or less horizontal there. So when I make it 10, it's very close actually. It's compressed by a factor of 10. And when I make it 1/10, something like 0.1, there, now it's 10 times further. And there we are. This vertex is 10 times further from the axis than that one. So you can play along with this and see what happens. And very informative, decimals. So there we go. That's horizontal compression. Let's move on to vertical translation of a polynomial. This one is perhaps the easiest because we just add c. So in this case, we are going to add 10. And we just move it up or down. So I'll take the original function and I'll just add a c. So let's go back here and we'll call this one x squared plus 5x minus 1 plus c. And we put a slider c there. We'll take the slider b out and take this one out. Okay, so there's our original function. And now we're going to add c. As you add c or subtract c, it moves up or down. So it's just going up or down, and c is affecting how the function moves only in the vertical direction. In the horizontal translation, that's the final one. We have our original function, y equals x squared plus 5x minus 1, and that's right there. Let's just erase the c and take the c out. So there's the original function, and now we're going to put in another function which will become like this. If I want to shift it by a distance d, I put the d in there and I solved the equation or simplified it, and I get x squared minus 2d minus 5 times x. Look at this. X times x is x squared. X times d and x times d is negative 2d because there's a negative. And then negative d times negative d is positive d squared. Then we have a plus 5, which is negative times negative. There's the 5 times the x. And we have a minus d minus 1. So if you expand this, you get this. You might want to try that to make sure you can see how this one is equal to this one, or expression rather. So how this expression is equal to this expression. So now we have a general form where we can put any value of d and find out what happens. In this case, let d equal 3. We're going to move the function horizontally by a distance of 3. And there we put 3 into the equation. 2 times 3 is 6. And 3 times 3 is 9. And 5 times 3 is 15. Simplifying, we get this one. So I'll put this in our equation and see what we get. So there we are. There are two identical equations, except that one is translated by a distance of 3. There's negative 2.5 for one vertex, and here's probably 0.5 for another vertex. So you see the distance between them is 3. So now we can also see this one. We will put in the value of d. So I'm going to try putting this one in our equation, see what we get. Oh, it didn't like that. It didn't just copy and paste now, did it? Try one more time. We may have to just type it out. That's okay. So it's going to be x squared, x minus d squared, okay, I didn't simplify it, but I put a slider d in here, and there's d equals 1, and it's move over by 1. If I make d equal to 0, I get the original. If I make d equal to 3, I get the other equation that we just did. So we can see how d only allows the function to move sideways. And so there's a horizontal translation by d. When d is positive, it goes in a positive direction. When d is negative, it goes in a negative direction, but remember there's a negative sign in front of the d. So that's horizontal translation. And this is for polynomial equations. So we've seen 4 types of transformation for polynomial equations. Let's move on to some trigonometric equations. And here is a times sine of k times x minus d plus c. In this case, we put all 4 of the transformations together. But for trigonometric functions, you'll see that the horizontal compression or stretch, B, is changed to K because it's convenient for indicating what is the period. And we'll get into this in the class. So instead of using B, we use K, and K is basically 2 times pi divided by B. So I'm going to put this into the Desmos, and we'll have sliders for A, K, C, and D, and we'll see what happens to our sinusoidal function. So in this case, we're doing all of the transformations together. We'll explore them one at a time. I'm just going to put them together to give you a big picture of where we're going. So let me just erase the previous functions here. Let's try this. Y equals A times sine of K times X minus D plus C. And we'll put a slider in for each one. There we go. I could have pressed all there. And I have to zoom out a little, and there is a function. Let's make C equal to 0. So now it should center vertically about this x-axis. I'm going to make D equal to 0, so it's not shifted horizontally at all. And then K is equal to 1. So that means that the period should be 2 times pi. So when it comes up here, 2 times pi is about 6.28, and that's where we are there. From here to there is 6.28 because the period is now pi. And A is 1. So vertically, it's not stretched at all, so it goes from -1 to 1. So now let me move it up or down. Good. I can move it up or down. If C is 0, it's back to where it was. I can move it side to side. Whoa, waves on the sea. It looks like water on the sea. Put that back. Now K is a little more fun. It will stretch it out. It's like a spring almost. So you can play with values of K and see what happens when they're big or that's positive or negative. The period gets very short. When they're small, the period gets very long. And when it gets close to 0, it almost has an infinite period. And finally, A is equal to 1. Let's put this back to like a normal value of like 1. And let us expand it vertically and negative, upside down and right side up. And when it gets close to 0, it gets to almost a flat line, and then it goes back. So look at the power of Desmos to understand almost your whole mathematics course in just a few minutes of playing around. We've almost covered all of the major functions we're going to see. The last one here is the exponential function, and we're going to apply the transformations one by one. So in this case, I just named A, capital A, as the vertical stretch because we're using A as the exponential base here. So we're starting with powers of 2. The exponential base, A, is 2. So the example says A equals 2 there. So we start with 2 to the x, which is A to the x. And then we're going to apply a vertical stretch by factor 3, a horizontal compression by factor 4, a vertical translation by 1, and a horizontal translation by 5, or -5, moving to the left. So let's see those play out in the Desmos. Take out our sliders and our function. And y equals 2 to the exponent x. That's an exponential function. So 2 to the exponent 0 is 1. 2 to the exponent 1 is 2, and it's about there. And 2 to the exponent 2 is 4, and so on. 2 to the exponent 3 is 2 times 2 times 2, that's 8. So up here, it should be 8, 3 and 8, for example, and it continues like that. To the left, it's almost 0, but if you zoom in, you'll see it's not quite 0, but it's very close to 0. Wow, you have to zoom in quite a long way to show that it's not 0. Never hits 0, but it just gets ever so close to 0. So there is our exponential function. 2, 4, 8, 16, it just grows and grows and grows. So now our second function, we're going to go 3 times 2 to the exponent x. So now our intercept, our y-intercept, goes from 1 to 3. There's 1, there's 3. So now we've done a vertical stretch. We'll continue now, and we'll say y equals 3 times 2 to the exponent 4 times x. Oops, 4x. There we are. So now I've compressed it. The red one became the blue one. And so each point is now 4 times closer. So right here we have 1 unit from, if this is at y or x equals -1, this is at x equals -0.25. Each point is 4 times closer. And the final transformation, we're going to shift it by 5 and then by 1 horizontally and vertically. So let's try that one. Y equals 3 times 2 to the exponent 4 times x minus, or is it plus 5? I think I said plus 5 now, didn't I? To the left, yes. Okay, and the final one here, we're just going to add 1. Okay, so there are all the transformations. The original graph here is in black. The next one is in red, and it's 3 times the distance from the x-axis. The next one is in blue, and each point is 4 times closer to the y-axis. Then we shift it to the left by 5, and finally we move everything up by 1. So those are the transformations on the exponential functions. So this video shows the idea of transformations of functions, but it covers material from the entire course. So now you can start learning about the different types of functions by reviewing the material in this video. I recommend doing this with Desmos so you can try for yourself and understand how these transformations work. So if you know how to do compressions and stretches and translations for all the different types of functions in the course, then you're a good part of the way through the material of the course. So this video is teaching the most important ideas first. So hopefully you will be able to learn a lot just from this one video and have fun trying all of the different possibilities in the Desmos Graphing Calculator and learning about these transformations of functions. There we go. That's enough for now.